Okay, I plugged in a microphone for this video to see if that works a little better. Sounds like the audio might be a little better here. So moving on to naming similar triangles, the second part of this lesson. Learning goal for today, we are going to determine if two shapes are similar. We're going to do that by using three different methods. First method is going to be one by angle, 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 or just AA for short. For two, we're going to determine if they are similar by taking a look at the side, angle, side, SAS for short. And our third one we're going to take a look at to see if two triangles are similar will be side, side, side. So those don't mean a whole lot right now, but you can see as we get into the lesson, we're going to show you what each one of those mean. First, we have to get some language similar, congruent figures. So if two figures or triangles in this particular case are congruent, we're saying they're the exact same triangle. They may be rotated or flipped or something like that, but you could pick one triangle up and you could lie it directly on top of the other triangle. So that would be same shape and the same size. What we're going to take a look at more often than not are similar figures. So similar figures are almost the exact same thing. They're just usually a scaled up or scaled down version of each other. So if we take a look at one of these two triangles here, while we can see they are the same shape, they're just a different size. So properties of similar triangles is that similar triangles have three equal angles. The ratios of corresponding sides in similar triangles are equal, and the ratio of the areas of the triangle is equal to the ratio of the square of the corresponding sides. So let's take a look at one of these problems. First way we're going to prove two triangles are similar. Okay, they're the same triangle, just a scaled up or scaled down version of each other, is by angle, angle, angle. While we only say angle, angle, if you know two of the angles in a triangle, obviously you can find that third angle out pretty quickly. So if we take a look at this triangle here, we can see that angle A is the same as angle D. So this triangle, 30 degrees, is the same as this triangle, 30 degrees. We can see that this angle here, 60 degrees, same as that angle, 60 degrees here. That's all we need to know. You can also prove that, hey, they both have a 90-degree angle, 90-degree angle. So once you know that two of the angles are same in the triangle, we can call them similar because obviously that third one has to be the same as well. So we'd say that triangle ABC is similar to triangle DEF by angle, angle. You could add an extra A on there saying angle, angle, angle. No real need, but those would be similar triangles. Second way we're going to prove two triangles are similar is by taking a look at one of the angles and two of the side lengths that enclose that angle. So what I mean by here is we have a side, an angle, and a side length. Those are what we know. And notice how that angle is enclosed by the two side lengths, or the two side lengths come from the angle that we know, and that's important. If we had a different angle in this diagram, then we wouldn't be able to use SAS. It's very important that that angle is enclosing those two sides. So if we take a look at the ratio of the sides, so we can clearly see that 75 and 75 degrees are equal to each other. So they both have a 75-degree angle. That's perfect. Then we take a look at the ratio of the sides. So if we take a look at AC, let me highlight that one here, AC, and we compare it to XZ, we can see that 21 is not the same as 14. significantly larger than 14. But if we take a look at that ratio and say the ratio of that is the same as AB, right here, 15, and, whoa, 10 degrees, or sorry, 10 length, will have the same ratio. So if we were to reduce both these fractions, we can take a look at 15 over 10 would be the same as saying 3 over 2, and 7 goes into both of those, 3 over 2. And we can see the ratio is the same. So this triangle ABC is a scaled up version of XYZ. So we multiplied both the sides by the same amount to get triangle ABC from triangle XYZ. So we would say that is similar triangles because a side, an angle, and a side are similar. Next way we're going to prove two triangles are the similar triangles is by taking a look at 3 of the side lengths. If 2 triangles have the same 3 side lengths, they're going to be congruent. Or if one triangle has the same scaled up side lengths as another triangle, then they will be similar. So if we take a look at this triangle here, we're going to say for side, 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 notice we don't have any angle measurements here, that if we take a look at triangle ABC, then we're going to say that triangle is similar to triangle XYZ. And let's take a look at why we're saying that. So length AB is 4 units long. Is 4 units long is what we're going to say very similar to YXY is 5 units long. So that ratio is 4/5, or another way to think of it is what is the scale factor? What do we multiply 4 by to get up to 5? 4 times something is equal to 5. We would say that scale factor would be 1.25. If you do 4 times 1.25, you're going to get 5. So then we take a look at another side, see if a different side has that same scale factor. If I take 6, so BC, and take a look at YZ, did I multiply 6 by 1.25 to get 7.5? And you'll see, yes, 6 times blank equals 7.5. It is indeed 1.25 again. And you can probably see where I'm going with this. My third side length, AC, is the scaled up version of XZ. So if I take a look at 8 and I multiply 8 by 1.25, I'm going to get the answer of 10. 8 times blank is equal to 10. Notice all 3 of those blanks, I fill it with the same value of 1.25, or we take a look at those 3 ratios there. 4/5 is equal to 8/10 is equal to 6 divided by 7.5. Those are all the same ratio. So it's been scaled up by this, all 3 sides have been scaled up by the same amount. All right, moving on. Let's take a look at some of these problems here. If you want to pause the video and try some of these out yourself before I write in the answers, I'd suggest going for that. Okay, so triangle ABC. If we look at triangle ABC, it's the bigger triangle here. And we're saying that is going to be congruent to triangle, let me switch colors here, AUV. Why? So we say that triangle ABC is congruent to triangle AUV, and that's through one side obviously they share this angle. We don't know if that's 90 degrees. I guess I shouldn't write it 90 degrees, but they both share this angle here. So that angle is the same, and that second side length has been multiplied by 3. So our scale factor would be 3 there, and triangle ABC is similar to triangle AUV. And we take a look at number 2. How are these two triangles similar? So I'm going to say that triangle VUT, so I'm going to do it in this particular order, VUT is similar to triangles FED, and we're going to take a look at how. It's similar to triangles FED. So we're saying that this 6 has been multiplied by something in order to get 42. What did we multiply 6 by to get equal to 42? Then we take a look at the next side. We needed to multiply this 5 by something to get 35. 5 times something is equal to 35. What did we multiply 5 by to get the answer of 35? And you can probably see where I'm going here. 8 times something is equal to 56. So is all of these numbers the same number? And we can clearly see, yes, all of those must be 7. So that scale factor is 7, or we'd say triangle FED multiplied by 7 would equal to triangle VUT. Therefore, they are similar triangles. Next one here, let's take a look. We can take a look, since we don't know any of the angles, while that does look like it is 90 degrees, that angle at J and A, it hasn't been labeled there, so we're not exactly sure. So we take a look at the side lengths. So if I'm taking a look at side C, or triangle CBA, let me highlight that one here. CBA. It looks like that triangle may, just may be similar to triangle CKJ. So let's take a look at this scaling factor. What did we do to side length 30 to get up to 50? 30 times something is equal to 50. Does that scale factor hold true for everything? Is 24 times something equal to 40? 24 times something equal to 40. And our last one, 18 times something needs to be equal to 30. So 18 times something needs to be equal to 30. So you guessed it, if we take a look at all of these, they have the same scaling factor of 1.666 repeating, or 1 2/3. So if you multiply any one of those numbers by 1 2/3, you're going to get the same answer as the larger triangle. So we say triangle CBA is similar to triangle CKJ. And that would be through side, because we've proven that 3 sides are similar, or that they go up by the same scaling factor. Okay, so now we got a tricky one here where we don't share something directly in common. So if we take a look at our angles here, we know these are two straight lines intersecting each other. So those two angles must be identical. They have to be the same thing through our opposite angle theorem, our OAT. So then we have to take a look at our two ratios of our sides. So if I take a look at this side, 27 here, what do we need to multiply 27 by to get 36, or is the ratio of 27 over 36, I would solve that one quickly, is that the same ratio to get 39 to go up to 51? Would that be the same scale factor? So in other words, is 27 divided by 36 equal to 39 over 51? And if you had a calculator, you'd be able to solve this a little more quickly. I guess we could reduce this fraction, so technically this is 3/4. Is that equal to 39 51s? Definitely not. Those are not the same thing. So we would say, since that these are not similar, there's no way that that has been multiplied by the same scale factor. 1, 2, 3, 4. All right, once again, if you want to pause the video here and try out these next couple for yourself, go for it. So I'll take a look at the same one here. Number 5, we don't know any angles, we have to look at the sides. So 40 times what is equal to 50? Is that the same number that we use 20 times? 28 times something is equal to 35. And the same number as 52 times something is equal to 65. And we can see here that we have the same scale factor. All three of these are going to be 1.25 again, common scale factor here. So we would say triangle RST would be similar to triangle MLK. Should put a little triangle sign here. Number 6. And we have a bunch of angles labeled in here. First thing we could do very quickly is say, hey, this is our opposite angle theorem. So I know that that needs to be equal to that. So we do not know any of the sides. We only know that one angle is common between these two triangles. If we only know one angle, we don't know that third angle or that second angle common between those two sides, we don't have enough information to say it is similar, so we can say not similar there. Number 7. If we take a look at number 7, we can say that once again we have intersecting lines, so we can say that confidently that this is equal to this angle. I don't know what those two angles are, but I know they need to be equal to each other. Then we have parallel lines. Those two arrows represent something as parallel, so we could use our, I'm going to use my Z pattern first. So if I draw my Z here, I'm going to say that because those two lines are parallel, that this angle, interior angles in the Z, need to be equal. So those two angles are equal, so the angle at G and the angle at W are equal. And then we know that because we have two angles that are equal to each other in that triangle, that the third angle also must be equal to each other. 3 angles add up to 180 degrees. So we could say that triangle EFG is similar to triangle EVW. Triangle EVW. Notice the order in which I wrote that there. Very particular. And last but not least, we have number 8. So first thing I'm going to do in number 8 is say that E, these are two intersecting lines. Those are opposite angles, so they must be equal to each other. Then let's take a look here. What did I do to 30? Is this arm similar to this arm? What did I do to 30 to get 78? 30 times something is equal to 78. Or 78 divided by 30 is equal to something. Then let's take a look at my other arm. If it's the same scale factor on that enclosed angle, what did I do to 50 to get up to 130? 50 times something is equal to 130. This would be the same way as writing like the ratio 30 over 78. We need to check and see, is that indeed equal to 50 over 130? So are those being multiplied by the same number? Well, this one's easy to reduce. We can take a 0 off both of those and say that is the same as 5/13. And 30, we have 5 going into that, and we have 13 indeed going into that. So those are going to be the same ratio. Therefore, saying that triangle EFG is similar to triangle ERS. I had to think about what order to write that in there for a second. If you have any questions, please email one of your math teachers or drop by office hours. Thank you very much.